In 1939, four German scientists, Otto Hahn, Lise Meitner, Fritz Strassmann, and Otto Fritsch, made an important discovery that ushered in the atomic age. They found that an uranium nucleus, after absorbing a neutron, splits into two fragments, each with a smaller mass than the original nucleus. The splitting of a massive nucleus into two less massive fragments is known as nuclear fission. Here we show a fission reaction involving a slowly moving neutron and a uranium-235 nucleus. The reaction begins when the uranium-235 nucleus absorbs the neutron, creating a compound nucleus, uranium-236. When the neutron collides with and is absorbed by the uranium nucleus begins to vibrate and becomes distorted. The vibration continues until the distortion becomes so severe that the attractive strong nuclear force can no longer balance the electrostatic repulsion between the nuclear protons. In this case, the compound uranium-236 nucleus disintegrates quickly into barium-141 and krypton-92 nuclei and 3 neutrons. This reaction is written as follows. The first step is a neutron plus a uranium-235 nucleus transforming into a compound uranium-236 nucleus. The second step is the spontaneous decay of the unstable uranium-236 nucleus into barium-141 and krypton-92 nuclei plus 3 neutrons. This reaction is only one of the many possible reactions that can occur when a uranium-235 nucleus absorbs a neutron. For example, another possible set of fission products from the disintegration of the compound uranium-236 nucleus is xenon-140 and strontium-94 nuclei plus 2 neutrons. When a nucleus bursts apart, the fragments carry off energy, primarily in the form of kinetic energy. The energy carried off by the fragments is enormous and was stored in the original nucleus mainly in the form of electric potential energy. We can estimate this energy using the graph of binding energy per nucleon versus nucleon number. Let's assume a nucleus with A equal to 240 fissions into two equal fragments, each with A equal to 120. Referring to the graph, the energy per nucleon of the nucleus with A equal to 240 is 7.6 MeV, and the energy per nucleon for each of the two fragment nuclei with A equal to 120 is 8.5 MeV per nucleon. The difference, 8.5 MeV minus 7.6 MeV equal to 0.9 MeV, is the energy released per nucleon of the fragments. Therefore, the total energy released is 0.9 MeV per nucleon times 240 nucleons, which equals 200 MeV. Thus, an average of roughly 200 MeV of energy is released per fission of uranium-235. This energy is more than 100 times greater than the energy released per molecule in an ordinary chemical reaction, such as the combustion of gasoline or coal. Virtually all naturally occurring uranium is composed of two isotopes. These isotopes and their natural abundances are 99.275% for uranium-238 and 0.720% for uranium-235. Although uranium-238 is by far the most abundant isotope, the probability that it will capture a neutron in fission is very small. For this reason, uranium-238 is not the isotope of choice for generating nuclear energy. In contrast, the isotope uranium-235 readily captures a neutron in fissions, provided the neutron is a thermal neutron, meaning its kinetic energy is about 0.04 eV or less. The probability of a thermal neutron causing uranium-235 to fission is about 500 times greater than the probability for a neutron whose energy is relatively high, say 1 million electron volts. Thermal neutrons can also be used to fission other nuclei, such as plutonium-239. One might ask, why not use other particles to induce fission reactions, such as alpha particles or protons? The answer has to do with the electrostatic forces involved. Uranium, with atomic number 92, has a total nuclear charge of plus 92 E. An alpha particle has a charge of plus 2 E. Therefore, the Coulomb repulsion at a separation r between the nucleus and the particle is K times 2E times 92E divided by r squared, which equals K times 184E squared divided by r squared. Therefore, the Coulomb repulsion gets very strong as the separation decreases, and the particle would have to have a very large energy to get close enough to the nucleus to cause a nuclear reaction. The situation is similar for a proton, which has a charge of plus 1e, resulting in a repulsive force of magnitude k times 92e squared divided by r squared. The reason why neutrons are so effective is now clear. They are electrically neutral. This means that there is zero repulsive electrostatic force between a neutron and the nucleus, and the neutron can strike it without resistance. The uranium fission reaction releases 2.5 neutrons on the average, which makes it possible for a self-sustaining series of fissions to occur. Here we show a neutron-induced fission reaction of a uranium-235 nucleus, which releases energy and 2 or more neutrons. Here we show only 2. If other uranium-235 nuclei are nearby, the 2 neutrons released from the first reaction can cause 2 of them to fission. Those 2 each release energy and 2 neutrons, for a total of 4 neutrons, which can now cause 4 uranium-235 nuclei to fission and release energy, along with 8 neutrons. The number of fissions and released neutrons multiplies quickly. This is called a chain reaction. With an average energy of about 200 million electron volts being released per fission, an uncontrolled chain reaction can generate an incredible amount of energy in a very short time, as happens in a nuclear bomb. It would be difficult to use a fission reaction to produce energy if it couldn't be controlled. By using a material that can absorb neutrons without fissioning, it is possible to limit the number of neutrons in the environment of the fissile nuclei. In this way, a condition can be established whereby each fission event contributes on average only 1 neutron that fissions another nucleus. Thus, the chain reaction and the rate of energy production can be controlled. The controlled fission chain reaction is the principle behind nuclear reactors used in the commercial generation of electric power.